Right. Thank you, Akshay, so much. And yeah, take it away.
Thanks for inviting me for this talk. And today I'll be talking a little bit about my work on concept bottleneck models and also generally interpretability, and then more specifically on this paper on concept bottleneck sparse autoencoders. And so I'm a PhD student in the Trustworthy ML lab at UC San Diego, advised by Professor Liddy Wang. And I'll talk a little bit about uh, what's the motivation of my research, and then a little bit on a quick overview of my research work, and then we'll go into some more details about the CB-SAE paper. And so one of the initial things that I started with was about neuron interpretability. And so there's a lot of work on neuron interpretability where the goal is to associate individual neurons with human understandable concepts. So let's say you have a neural network that you want to explain, and you're looking at individual neurons and trying to understand what they represent. And so there's methods like network dissection or clip dissect, which will say like, okay, maybe this neuron is representing a parrot, like it activates on images of parrots. And so this kind of works with a fixed concept set. Then you have like other kind of explanations, like linear explanations, where instead of having a single concept, you now consider it like a linear combination of multiple concepts. And then you can have, if you don't want to have fixed concepts, you could also go for open-ended LLM concepts. And there's methods like Milan and describe and dissect, which can give you these kind of explanations. But then like this is all well and good. And then how do you actually use these explanations? And so if you look at these original papers, they'll talk about sort of model debugging or interventions. So you can go into the trained model and try to change some of its decisions based on which neurons are activated. Another kind of application is bias or spurious correlation discovery. And so again, you can try to understand and control already trained models. And so some of my work tries to go beyond these kind of standard use cases. And so one direction that I'll look kind of application is by design models, and then more specifically interpretable by design generative models. Another line of work is sort of how do we use these methods, these explanations to improve, say, robustness or performance or other aspects of the model. And the third aspect is like, can we also use these to evaluate other interpretability tools? And so in today's talk, I'll focus a bit more on interpretable by design generative models, and then also touch a little bit on how do we do this kind of meta evaluation of other interpretability tools. And so when we talk about interpretable by design models, we mainly talk about concept bottleneck models. And the idea is that we use a neural network to predict some human understandable concepts. So for example, for bird images, you'll have these kind of concepts like wing color or beak length. And then you use a classifier based on these concepts to predict the task label. And so the benefit is that you get a task classifier that's actually interpretable with respect to these concepts. But then what we saw is that like most of the CBM literature focuses on image classification models, and we wanted to see if we can extend this to generative models. And why would we be interested in interpretable generative models? Like we've seen a lot of generative model usage these days. So you have really strong image generative models like Stable Diffusion or Nano Banana. You can get really high quality images with text prompts. And you have, on the other hand, text generative models, which are also very powerful, and they can even actually use these image generative models as tools. But then these are actually black box models, and then there's very limited or no interpretability built into these models. And we wanted to sort of look at what are the problems with having these kind of black box generative models. So let's say you have a model that, given a prompt, it generates an image. There's not no real like safety mechanisms here. So if you want to check for harmful content, it can only be done post generation. In terms of trust, it's difficult to trust these kind of models because there's no transparency on how the generation is actually happening. And if you want to control this model, it's really difficult to do fine-grained edits without having external tools to do it. And so we want to contrast this with like an interpretable generative model. So let's say first you try to predict some interpretable concepts with a concept bottleneck, and then you use those concepts to actually generate the image. And now we can have better safety mechanisms. You can actually monitor generation through these interpretable concepts. You can find failure modes on like which concepts are not well represented in the data or in the model. There's like better trust because you have more understanding of how the model is working, and you can actually build some user trust. In terms of control, we also show that like with this concept bottleneck, you can actually do fine-grained edits based on manipulating these concepts, and you don't need any external tools to do it. And so I'll give a brief overview of like what my other research has been. And first, like on interpretable by design generative models, our first work was concept bottleneck autoencoder. And so we wanted to come up with a concept bottleneck framework that could be trained post hoc with a frozen pre-trained generator so that it's much less expensive to train. And then you also get interpretability as well as ability to sort of steer generation. Then, like in the follow-up work, which we'll discuss a bit more today, we have a concept bottleneck sparse autoencoder, and here we wanted to combine unsupervised concept discovery with SAEs, with the supervised concepts of CVMs, and then we also show that you can actually do concept bottleneck steering in large vision language models like Lava. Another line of work was in like adversarial robustness. So we had a work in ECCV in the last year where we came up with this interpretability guided adversarial defense. And what we found is that if you use these neuron interpretability methods to figure out which neurons are important to which classes, you can actually mask the unimportant neurons and improve adversarial robustness at test time. Another kind of line of work is on interpretability tools, where we came up with this describe and dissect approach, where a pre-trained image captioner and large language model can be used to get natural language concept descriptions for individual neurons. And another work which is still in the pipeline is in inversion anchored CAVs, where we have these kind of concept activation vectors, and we are able to efficiently compute them to steer diffusion models like stable diffusion 3.5, and we can get these kind of steering results where we can steer specific attributes in a fine-grained way. And I wanted to briefly touch upon the concept bottleneck autoencoder paper, since that is also related to the CB-SAE paper. And so here, like the key idea was to transform a generative model into an interpretable model with steering capabilities. And we came up with this autoencoder setup. So where we have the concept bottleneck in the latent space of the autoencoder. And we just want to reconstruct the latent and not have to retrain the entire generative model. And then at inference time, what we see is that like with every generated image, we now have sort of these concept predictions. You have some interpretability on like which concepts are present in the image. And then you can also go in and do some concept interventions. So for example, here, if I wanted to change it from not smiling to smiling, I can go in and actually change those concepts and then try to generate the image again. And what we find is that you can actually get really good fine-grained edits. And so you can do this with like other attributes as well. So like from male to female, or not smiling to smiling, or mouth closed to mouth open. And this also works for the cub data set with bird images. And so we have the paper and the code already available. So if you are interested in this work as well, please feel free to take a look at the code. And so next, we'll go into some more details on the concept bottleneck SAE paper. And so this work was done during my internship at Lawrence Livermore National Lab, and we'll be presenting this at CVPR this year. And so the key idea here was we were looking at sparse autoencoders and what limitations it has. And then we tried to overcome those limitations with user-defined concepts and trying to improve the steerability. And so just some quick introduction on like what sparse autoencoders are. So let's say you have model activations from some layer L, which is like say 1024 dimensional. Then the sparse autoencoder has a linear encoder-decoder pair, which sort of projects the activations to a higher dimensional space. So let's say to some 65K dimensional space. And then the decoder reconstructs the latent back to the same input dimension. But then you also want to have some kind of sparsity constraint on the latent. So let's say you want only 20 of the latents to activate at any given time. And then we can actually train this with a simple reconstruction loss and some sparsity constraint, like in the L1 loss. And then after training, like what we find is that if you look at sort of top activating images for some of these sparse neurons, we find that like they activate for some kind of monosemantic concept. So for example, there could be a neuron that's activating on these pencil images, or another neuron that's activating on these koala bear images. And so sparse autoencoders can perform these kind of unsupervised concept discovery with these sparse neurons, or like the decoder columns representing individual concepts. And then we looked at some prior work on SAEs for multimodal large language models. And there's this work that trains an SAE on the vision encoder of a multimodal LLM. And here, if you train only on images, at test time, you can actually even steer the multimodal LLM. So for example, here you have a neuron that say represents pandas. And if you steer this neuron and the image is of a cat, you can actually get the output to change to it as a panda. And so this is really interesting that like, even though you only change sort of the vision side of things, you can actually still uh, manipulate the large language model. And so we wanted to look deeper into this. And one of the questions we had is like, since there's such a huge number of SAE latents, like the 65K dimensions, how many of these are actually interpretable and useful for steering? And then another question we had is like, how many of the SAE latents are unique and not redundant? Since there's such a huge number of neurons, it's really difficult to manually go through them. And so we came up with some analysis experiments to answer these two questions. And so just before that, like going back to the neuron interpretability idea, since that's really useful for this kind of analysis, if we have, say, an explanation from network dissection or clip dissect, it also comes with some kind of score. That could be like a intersection over union score from net dissect, or a similarity score from clip dissect. And this actually enables us to quantify the interpretability of the neuron. And we can use this even with the sparse autoencoder. So this is some kind of meta-evaluation that we can do. And so this is what we use to sort of answer the first question on like how many SAE latent neurons are interpretable and also useful for steering. So we start with, say, an SAE baseline that's already trained. And we use a neuron interpretability tool like clip dissect, and that gives us an interpretability score for every SAE neuron in the latent space. And then we also do some downstream steering evaluation. So for example, with the Lava multimodal model that's in the previous work, and we can get a steerability score on how well we can steer each individual SAE neuron. And with this, like we can actually plot a heat map, a distribution of like how the SAE neurons are behaving in terms of interpretability and steerability. And so this is like a scatter plot of all of the SAE neurons. And what we find is that a really high number of neurons actually have very low steerability and interpretability. So almost 36% have very low steerability and interpretability. And if you look at the overall picture, then a majority of the SAE latent neurons, like about 81%, are actually not always useful for downstream tasks. So either if you want to do interpretability or steerability, there's like a huge number of neurons that are not actually good for that task. And so this sort of represents a major limitation of the SAE. Now for the second question, we were asking like how many of the SAE latent neurons are unique. And what we can do is like we can look at say a neuron interpretability tool like clip dissect, and we can try to figure out how many unique concepts are represented in the SAE. And this analysis we did for an ImageNet trained SAE with 65K dimensions. And so we looked at different concept sets with varying sizes. And we looked at how many of the how many concepts are uniquely represented in the SAE, and whether all of the concepts are actually covered. And that's what we show here with the coverage statistic, like how many of the concepts in the concept set are actually present in the SAE. And what we sort of find here is that as the concept set size increases, that's from top to bottom, we see that the SAE concept coverage actually drops. And even though we trained the SAE on ImageNet, there's like some ImageNet related concept sets which are not completely represented in the SAE. And also, like one important thing is that the concept set sizes are all less than the dimension of the SAE. And so it's still not able to completely represent all of the concepts. So there's a lot of redundancy in the concept set. And let's say you want some concept that, let's say you have some concept that you want to steer or interpret, that might actually be absent from the SAE. So that's another limitation of the SAE. And so we find these two limitations of the SAEs, and we wanted to address them with our method. And so the first limitation is that a lot of SAE neurons are not actually useful for downstream tasks. And the second one is that concepts of interest to users might be absent from the SAE. And so to address the first limitation, we try to come up with a way to prune these low interpretability and steerability neurons. So since we already have the analysis where we are able to get some interpretability and steerability score, we can actually prune the SAE. So we get rid of the M least interpretable and steerable neurons. And this is easy to do because of the linear structure of the SAE. So you can easily delete the encoder and decoder rows and columns. And you can get rid of these low interpretability, steerability neurons. But then by doing this, we actually lose some of the reconstruction ability. And then we have the second part of the method, which sort of helps us to recover that. And so the other limitation was that some concepts of interest might be absent from the SAE. And so we come up with this way method to like add a linear concept bottleneck autoencoder alongside this SAE. And this will incorporate all of the concepts that are missing from the retained SAE. And now, like we also need to train this concept bottleneck to make sure that we are able to reconstruct the latent. So now we'll get into sort of how the training works. And so in this training process, like we always keep the pruned SAE frozen. And since we have added this new concept bottleneck autoencoder, we need it to be able to reconstruct the latent. And so we have a latent reconstruction loss, which is like an L2 loss similar to the original SAE. And this helps us to like recover the reconstruction ability that we lost during the SAE pruning. So this is the first reconstruction loss that we have. Next, since we wanted the concept bottleneck to predict the concepts that are absent from the SAE, we need some kind of supervision. And so one way to do that is to use a clip zero-shot classifier. And with the user-specified concept set, we can get pseudo ground truth concepts for those concept sets. And then we have a cross entropy loss to be able to predict the concepts correctly. And so this is an interpretability loss that we add. And so, yeah, so this helps us to learn the concepts that are absent in the pruned SAE. Next, we also have a steerability specific objective. And the idea is to use a cyclic reconstruction objective. And so after reconstructing the latent, we can pass it back through the concept bottleneck layer to the concept bottleneck encoder, and we get back the concepts. And we want them to actually match with the pseudo ground truth concepts that we computed earlier. But the key thing here is that we keep the encoder frozen so that the decoder gets some supervision from the concepts to like, how do you actually reconstruct the concepts? Because originally in the interpretability loss, we did not have any supervision for the decoder from the concepts. And so this helps us to encourage the concept bottleneck to also be steerable. And so we have these three losses, which each target a different ability that we want the CB-SAE to have. Now we can like get into some of the experiments that we did. And so we trained SAEs and CB-SAEs on CLIP VIT as well as Dino V2 image encoders with the ImageNet dataset. And we show that like training on just the image encoder, we can use the same SAE or CB-SAE on different downstream tasks. So for example, we can have a multimodal large language models, for example, Lava, which could have a clip VIT or a Dino V2 image encoder. And we have the SAE on the vision encoder, which then goes to so the encoded tokens then go to the LLM, and we can do visual question answering tasks with this. The other downstream task we have is an image-to-image generator, where we have a unclipped model with stable diffusion that uses a clip VIT image encoder. And again, here we can use the SAE or CB-SAE to do image-to-image generation. For quantitative eval, we consider two metrics. So one is an interpretability metric, like clip dissect similarity score, and the other is a monosemanticity score, which we borrow from the previous paper. And this sort of highlights like how interpretable all of the individual SAE or CB-SAE neurons are. And the other metric is like a steerability metric. So whether we are able to successfully steer. And to measure this, we look at the similarity of the steered output to the intended concept. And so these are some of the main results we have. So for example, for Lava 1.5, we find that CB-SAE can improve interpretability by about 7% and steerability by about 6%. Then we have another Lava model with a Dino V2 image encoder and a Gemma 2 LLM. And here we also are able to improve interpretability by about 7% and steerability by about 2%. Then we have an unclipped image-to-image generator with a clip VIT encoder and a stable diffusion 2.1 model. And here we are able to improve interpretability by about 3% and steerability by about 1.5%. And so, yeah, so CB-SAE has sort of consistently better interpretability and steerability than the SAE baseline. And next, we also show some qualitative eval on how the steering results look. And so when we talk about steering, what we mean is that we are highly activating individual neurons, and then we try to check what's the Lava text output and whether that matches with the intended concept. And so there's three sort of categories of neurons. So one is the neurons that we have, one is the SAE neurons that we have discarded during pruning, and the ones which we have retained after pruning. And then we have the concept bottleneck neurons that we had later during the CB-SAE training. And so let's say you have some neurons with concepts like chocolate syrup or race. And what we find is that after steering, the Lava model actually outputs the cookie, which is like partially related, or truth, which is not exactly related. Whereas like for the retained SAE, we see that like there's concepts like bathroom and bread, and then the Lava output actually exactly matches with the intended concept. Similarly, for some concept bottleneck neurons, we have concepts like face or rubber or mansion, and actually Lava is able to correctly we are able to correctly steer Lava to predict the same concepts. And so overall, what we found that the CB neurons and the retained SAE neurons have much better steerability than the discarded SAE neurons. And that's natural because we have the pruning that's based on steerability itself, and we also have the concept bottleneck neurons with some steerability objectives. So they are able to get better steerability. Next, we also show some qualitative eval on steering the image-to-image generator. And again, here we are highly activating individual SAE or CB-SAE neurons, and then we obtain the unclipped image output. So again, we have these three categories of neurons. And let's say there's some concepts like made of pores or fishbowl in the discarded SAE. And if we steer those neurons, what we find is that the images are either very noisy or it's not actually related to the concept. Another kind of in the retained SAE, there's concepts like desert or leather or fabric, and then the steered output actually does correspond somewhat to those concepts. And then for CB neurons, we have concepts like cross or blunt edge or windows. And then after steering, we do see that the images do represent those concepts. And overall, what we found is that the CB neurons specifically produce more realistic and less noisy images than the SAE neurons. And so another kind of eval we wanted to do is like, since we were looking at this kind of scattered plot of how the SAE neurons are on the steerability and interpretability axis, we wanted to also look at how the concept bottleneck neurons are doing in this aspect. And so first we look at sort of the retained SAE neurons. So after pruning, we actually do get rid of all of those low interpretability and steerability neurons, and we can still keep some of the neurons that are actually good for steering or interpreting. And then when we look at sort of just the concept bottleneck neurons, we see that like actually they have better interpretability on average and slightly better steerability, but then there's more number of SAE neurons that have higher steerability. And so one of the things that we still want to explore in the future is like, how do we improve the steerability even further for the concept bottleneck neurons? And one way we think is that we might need to have more task-specific objectives for that. And so in the current setup, we did not actually have the downstream task involved in the training. Another kind of analysis we did was sort of trying to ablate the SAE itself. So whether do we actually need the SAE in the CB-SAE framework? And what we found is that removing the SAE actually hurts steerability. So you can see the steerability drops a little bit. But then the CBAE without the SAE actually has a higher interpretability score because this concept bottleneck is actually optimized for the clip dissect score. Next, we also look at sort of across different types of SAEs, how does it compare? And for most of our experiments, we use the state-of-the-art Matryoshka SAE. But then for this particular analysis, we also looked at top K SAEs and batch top K SAEs. And what we found is like somewhat interesting, where actually the older SAEs do have higher interpretability scores. They also have higher steerability scores. But then if we look at the dead neurons, which is like there's a lot of SAE neurons which don't actually activate on any inputs. This is like another major limitation of SAEs. And so Matryoshka SAE does solve that problem, but at the cost of a little bit of interpretability and steerability. And then we also looked at like what's the corresponding CB-SAE performance for these types of SAEs. And what we saw is that like our SAE pruning is actually able to remove these frequently activating neurons. And so the dead neuron problem is actually resolved even if we use the top K or batch top K CB-SAE. And the other thing is that indeed like the CB-SAE is able to consistently outperform each type of SAE on steerability or interpretability. And so yeah, in summary, like we came up with these, we found these two important limitations of SAEs. So one is that a majority of SAE neurons are low utility and SAEs have limited concept coverage. And and we tried to address these limitations with our concept bottleneck sparse autoencoder. So we are able to prune low utility SAE neurons and also enable user specified concepts. And we show that this generalizes across large vision language models and image generative models. And our paper is available on arXiv, and our code will be made available soon at this link. So if you're interested, please feel free to check those out. And so yeah, thanks for listening. And if you have any questions, I'm happy to take them now.
Thanks so much. That was fantastic. Yeah, if you have questions, yes, Aya, please go for it.
Very, very cool talk. So I wanted to ask, can you go back to the interpretability and steerability metrics, please?
Yeah.
Can you explain the interpretability metrics? The clip dissection one?
Right. So here, like we're just looking at the similarity score that clip dissect gives us, and we can compute this for every individual SAE neuron, and then you can average that over all of the SAE or CB-SAE neurons.
Okay. But why would we like why would we assume that they would be very similar in a sense? Because SAEs are trained differently, right?
Uh, no, so what we are looking at is so clip dissect is comparing the activations of a particular neuron to sort of the uh, clip image text scores for a particular concept. And so we are looking at only the highest, only the similarity score for the concept that has the highest similarity. And that sort of represents like how well does this neuron represent this concept. Uh, so that's what we are looking at.
Okay, so you pass multiple images through both, right? And then you basically calculate the similarity score for a given concept
Yeah.
on every single neuron. So similar to like what you would do in the auto interpretability framework for SAE, but except here you're comparing two clip.
Yes.
And basically the goal is to have more concepts with a higher threshold. That would that would score more on this metrics.
So basically for one neuron, let's say it, maybe I'll go back to like some other slide, this slide, I guess. So let's say this neuron is like an SAE neuron and it has the concept predicted as parrot. And then it has some score, say similarity score 2.5. Then we want the score to be as high as possible so that this neuron is actually representing parrot in a sort of a monosemantic way, or like it's only activating for parrot, it's not activating for other concepts.
Okay. And yes, okay. And the steerability score is basically how much you, when you steer that, when you change the neuron, you get a change in the output.
Yeah. So if this neuron is for say a parrot concept, then steering that should also give us something related to the parrot. And so yeah, so we are measuring that similarity.
So in your steering, you're also measuring how much it's related to like a prototype class of parrot, not just that it changed the images.
So it depends on like the downstream tasks. So for example, with
so
yeah,
you,
with the
CUB, for example, you said CUB, right? You did, or no, you here it wasn't CUB. You were doing something else.
right, like here we are looking at a visual question answering task. So like we might ask like what is in this image, and we try to steer say the parrot neuron, and so we want the LLM to also say then like parrot or bird, and so that would be like a good steering.
Okay, and you used so you mentioned you had a cyclic loss, right? You used the cyclic loss you had to basically make sure that the output would like when you were training your CBM version of it.
Yes.
So I'm wondering why you think it wasn't enough to solve the problem of that there were a lot of things that were still not steerable the way you thought they were.
Yes. Yeah. So I think that like here, it's more of an implicit way to encourage steerability. So like we do have some like ablations in the paper where including this loss improved the steerability. But then since the downstream tasks are kind of different, like we have say an LLM in the downstream task or an image generator in the downstream task, these are not actually used during training. And so if we could use these during training, that will sort of further improve the steerability. Currently, it's just like task agnostic. and so that might not be the optimal way to do it.
Okay. Thank you so much. Very interesting.
Yeah, thanks for the questions.
Hey, sorry, may I just add a follow-up question and then I'll let others ask questions. So when you have the figure of steerability, I think it was in the y-axis and interpretability on the x, could you mind going over to there? There was a
Yeah.
weird thing that I was wondering if you have any intuition for it. That line at the top, the fully steerable set of neurons. What with that?
Yes.
Like what's special about them? You have an intuition, or like do you take a look into those?
Yes. So so here what we are doing is like we are steering the lava model, and so the output is sort of text. And when we compare two text strings, let's say in a sentence embedding model space, if they are basically the same text, then you'll get a score that's like exactly 1. And if they are like synonyms or something, then you'll get a slightly lower score, or then the similarity sort of starts going down from there. So for these neurons at the top, that means that they gave exactly the same sort of text output that was also in the intended concept.
I see. So it's semantically the same, but just different output, but the same. Is that correct? Like, so just correct. Just understand. Steerability of 1 means that it is as steerable as it gets, right? Like it changes the output as much as like 1 here means most steerable. Is that correct?
Yes. Yeah. So basically, you have some concept set that like, okay, this particular neuron is say for the parrot concept. And when you steer it with lava, lava also gives you parrot as the output. So that would have a steerability score of 1, like exactly 1. If it had said, say, bird, then it would be like, say, 0.9 or 0.8, right?
Okay, I see. But still, like, why is there just that set of neurons that seem to be very steerable? Like, what's special about them?
Yeah, I think that's harder to say on like why there are these neurons, but then yeah, I think in terms of like the entire distribution, these are not as high as like we want. Like ideally, we would want all 4 quadrants to be sort of 25% uniformly distributed, but then these are actually not as high in number as say the low steerability or interpretability neurons. So
yeah, the reason why I ask is because then it could be like another explanation is that there's sort of an artifact on the metric used for steerability that sort of leads to that. So we may be reading the wrong things here. It's just a matter of like the way the metric is defined allows you to have this sort of weird behavior, so you should sort of maybe ignore them. But I don't know. I was wondering if you look into them, but obviously it's quite tricky to unless you do some
yeah,
time consuming
I think
analysis.
you're I think you're right. So we do have this kind of same plot, but with the image-to-image generation case. And there we don't have like a top line like this because there we are comparing images to concepts, like images to text. And so we don't have this kind of artifact. So yeah, it is indeed like because of comparing text to text versus comparing images to text, that kind of problem does arise.
Okay, cool. Thanks so much. Any other questions? Does anyone have any questions? Let me see.
I had a follow-up question.
Yes, go for it.
Yeah.
Yeah. How can one provably say that like the steering effect that you see stays intact over a range of different tasks? Like for example, any out of distribution task for let's say clip.
Right. Yeah, I think it's not. Yeah, I don't think it's possible to provably say it with this work. At least it's more of an empirical analysis. But yeah, it might be. Yeah, we might need more work to like uh, have theoretical support for this kind of steerability.
Okay.
Or like you could try to do some kind of statistical analysis on like whether it's consistently able to steer or not. So that could still be possible.
Hmm. How would you imagine like doing that?
So let's say you try to steer the same neuron multiple times, so let's say with different prompts or with different steering sort of values, or say with different random seeds, and you try to get some kind of average and standard deviation for that. So that might be a more rigorous kind of evaluation. But in terms of like the theoretical way, I'm not really sure how you would do it.
Okay. All right. Thank you.
Yeah, thanks for the question.
I believe you. Yeah, I believe you had a follow-up.
Yes. So I had a follow-up question to yours actually. So here uh, are the maybe the high steerable concepts are concepts that are very like distinct, that the LLM is very hard to be like they're either there or not. Like for example, there is a ball, so it is very clear, but other ones are more ambiguous concept. Like for example, if this is a certain type of rug. So I'm guessing, like I don't know, maybe these are like less ambiguous concepts, the ones that got high score. So I wanted to see um yeah, I don't know, this is one way. And also, if you change this downstream performance, did you look at like a downstream steering evaluation? I'm guessing you might get a very different plot based on this downstream performance. Like one thing is like, is it too much of fitting to this one downstream task?
Okay. Right. So for the downstream task, we did try it with the unclipped image-to-image generation task,
And you
and
got a
we
similar
do
plot.
have. Uh, Sorry, could you repeat?
It was a similar plot.
Right. So the distribution is not exactly the same, but what we found is that like the proportion of high steerability, high interpretability neurons, that is indeed quite low. So like, it was like maybe 10 to 15%. And so that sort of observation still holds, but the distribution where here it's like quite low in the corner, it was maybe somewhere here in the middle. Like I think you can definitely check it in the paper. Like we do have that plot. So the range of values does sort of change a little bit, but our sort of observation on how many high steerability, high interpretability neurons there are, that does remain valid across two different tasks. And we also have another experiment with a different Lava model with a different LLM and a different vision encoder, and there as well, the same observation holds.
Interesting. Thank you.
Yeah, thanks.
Does anyone have any questions? Because I actually have one. So just to confirm, when you do the tasks, like the sort of visual answering tasks, do you do, for example, like you had an example where it was like what color is the image or something like that, like which I'm not sure if that's all you did, but you had an example there to show the classification, the image question answering tasks.
Oh,
Like,
right.
do you actually look at text generation, or do you just look at the logits of the correct classes versus the other possible options and see which one is the highest? Or I'm wondering whether when you do this steering, the model just still correctly puts more probability mass in the correct token that should be output, but generates nonsensical token if you let it do it something, or is it actually generating the whole text correctly?
Okay. Yeah. So like here, I guess the detail here is that in the prompt we'll say like what is in the image, answer in one word, but we still let it kind of generate on its own. Like we don't restrict it to one token or one word. So we let it sort of generate open-ended. And we do find like most of the times it will generate a single word or like a few words. But if you sort of try to steer, like while steering, if you sort of increase the value too much or decrease it too much, it will start generating gibberish. And so that kind of problems do exist. But like generally it's well behaved. Like if you say answer in one word, it will indeed follow it because it has been trained for instruction tuning,
Okay, so it's been
instruction
instruction to it.
following. Yeah.
Yeah, I see. And
Yeah.
then I guess the follow-up question is then, have you guys tested like long contexts? Like at what point is the steering of the original tokens from your image sort of not meaningful for the steering to be effective, like efficient?
Uh, no, like we haven't tried that yet. I think yeah, that might be interesting to try. Yeah, but I think in the current setting, there's only like one image and one prompt, and so I think yeah, it might be possible that like if we increase the number of images or they increase the prompt length, that might start sort of falling off, and so you might need more work on like fixing that.
Yeah. Okay. Yeah, just wondering. This is perfectly fine as it is. I just wondering whether you
Yeah.
have tried, because I imagine it's one of those things that, yeah, a few words kind of make sense, but then eventually it just if you don't steer, if you're steering strong enough, it just generates gibberish. And
Yeah.
if you don't, then eventually it gets forgotten. So there's this weird trade-off which is very difficult to get to. No, that's very cool. All right.
Yeah. Thanks.
Any other questions? Alrighty. Let me see what time it is. Yeah, we're good in time. Okay. Well, if no one has any more questions, thank you so much. Actually, really appreciate it. It's been fantastic. Really appreciate your time, and thank you everyone for coming this week.
Yeah. Thank
Hopefully
you,
we'll see
everyone.
you
Yeah.
next week.